Hello guys, this video is going to be talking about blockchain and its relation to quantum devices. Below are the links to the two papers that these videos will be based off. First, I'm going to do a quick recap for those who missed the previous videos. Below on the screen are a bunch of bullet points about blockchain basics which you should already know from my previous videos. For transactions, there is an input which is the sender's account address for its public-private key pair. This is associated with the cryptocurrency or data that is moving to the output address. There is also a digital signature. This is created from the sender using its public-private key pair. This demonstrates ownership and authority over the data being transactioned. This data is then sent to a transaction pool. This contains all the transactions that have not been added to the blockchain but have been declared to the network. This means that they are not yet immutable and they are not considered part of that blockchain. This pool can be accessed from any node connected to the network. Primarily, proof of work or mining nodes are used. These nodes perform difficult work to prove that they should be the next miner to add a block to the chain. Proof of work can be any NP-hard problem which is difficult to calculate but trivial to verify in the opposite direction. The two major elements of blockchain that link to quantum attacks are ECDSA, elliptical curve digital signature algorithm, and proof of work. ECDSA is used to prove authority and ownership of the cryptocurrency being transacted. A public-private key pair is used to digitally sign each transaction, and it relies on the hardness of discrete logarithms. I'm not going to talk about what they are, but think of it as a difficult one-way problem. Easy to verify, but near impossible to reverse the meaning to solve the private key from the public key. Proof of work is generally an NP-hard problem. Again, difficult to calculate, but easy to verify. This produces a race to see which miner adds the next block. Its primary function is to slow down miners. This is because we don't want everyone adding thousands of blocks every second. UTXO can be considered more like cash, while ABB is more like a card. Alice needs to have a UTXO with some value amount of cryptocurrency stored on the blockchain within the history. When she declares a transaction, she will reference this UTXO there by spending it. Within the output, she creates the new UTXO. This output will be the new cryptocurrency that she sends to Bob. She will also create a change UTXO, which is her paying herself the remainder of the money not sent to Bob. A digital signature is also still needed. For ABB, Alice has an amount of crypto that will be associated with her public-private key pair. She then adds the addresses and the input. The output will be Bob's address, and then she determines the amount of the delta change in the amount of cryptocurrency. Every time Alice creates her change UTXO, she will normally create another public-private key pair for that new UTXO, while with ABB it is associated with one public-private key pair which gets reused. UTXO-based coins are Bitcoin, Litecoin, Zcash and Monero. ABB would be Ethereum. Through the use of superpositions and quantum mechanical magic, a quantum computer can run algorithms that are not possible on classical devices. I will make a series on quantum computing and cryptography, but I am building up to it, so for now, this is all you're going to get. Shor's algorithm is based on quantum Fourier transformation and can be utilized to calculate the solutions to discrete logarithm problems and factoring with an exponential speedup when compared to the best known classical methods. It reduces the amount time complexity to solve for a private key from its public key from approximately 2 to the power of n to n to the power of 4. If anyone doesn't understand this, just search about big O notation. This is important in relation to blockchain because elliptical curve digital signature algorithm. This is used to digitally sign and prove authority and ownership over the currency and is reliant on the hardness of discrete logarithms. Grover's algorithm is a quantum search algorithm, meaning that it can search an unstructured search space with quadratic speedup. An unstructured search space could be the entire search space for the keys for the public-private key pairs. It could also be an entire hash's search space, which is in relation to proof of work. Using classical methods, proof of work can be done in O(n). Using Grover's algorithm with quadratic speedup, it is O to the power of n, where n is d times 2 to the power of 32, where d is the difficulty of mining the given block, i.e. the computational power it requires. Quadratic and exponential advantages. If the computational power on the Bitcoin network currently was made up of all quantum devices, it would take 0.0016 seconds to mine a block, compared with the current 10 minutes. This is the advantage of quadratic speedup. In the 10 minutes to add one block, a quantum device could add 3.74 million blocks. In order to break RSA 2048, it would take a classical computer with 32 gigabytes of RAM and a 10 gigahertz processor 1.2 million times the age of the universe to break. It would take a quantum computer with 10 kilobytes of RAM and a 10 megahertz processor 14 minutes. I'm going to stop here and leave you with those examples so you can realize how at risk these blockchains really are to quantum devices and quantum intrusion. I'll continue in another video, and I really do urge you to check the links to the papers below, which is what this is all coming from. Thanks, goodbye.